Hello everyone and welcome to The Wild Side. This is your host Kight, back from California and broadcasting live for the first time in about 3 weeks, I think. So hopefully I remember how everything works. And today we're going to talk about a subject that I became interested in while I was in California. When we were there, we went to the Mojave Desert, among other places, and we visited some cinder cones and lava tubes. And these are the sorts of things I never ordinarily would go to see, but since I was with the University of Exeter Geography group, then I got involved with these sorts of things. And I don't really know much about volcanoes or geology or any of that kind of stuff, or at least I should say that I didn't, because I thought it was all really interesting and intriguing. And so I went out and I bought a book in order to read up on this and understand a bit more about the sorts of things that we were seeing. And so today I want to talk a little bit about volcanoes and kind of what they are, where they come from, what they do, what types there are. And I know that you guys in Britain tend to have a bit more of this kind of information in your education than we do in the US. And I know this because I've heard a lot of stories about people who've gone to Iceland, for example, to see volcanoes and volcanic activity while they were in school. And in fact, on my way home from the US, I encountered a school group that was on their way back from Reykjavik. And so some of you may have already heard some of these things in the past, but hopefully I will go into a bit more detail and throw in some facts that you've not heard before, so that by the end of today's broadcast you will know more about volcanoes than you ever thought you would, and maybe be inspired to go out and see some in person. So just to begin really from scratch, you might be interested in knowing that the word volcano comes from the name of the Roman god of fire, and he was named Vulcan. So from very early on we've used this word to kind of relate volcanoes to fire, which is really an accurate thing considering that volcanoes are associated with the escape of subterranean materials from the earth. Now some of these aren't really fiery, but of course magma, which turns into lava once it reaches the surface, that is something that's very fiery, and so that's what is really being evoked when you say the word volcano. So the other sorts of things that can come out of these ruptures that are what volcanoes are, they're just these cracks in the Earth's crust through which these materials can escape. And that includes not just magma, but also volcanic ash and gases. So magma is a mixture that contains molten or semi-molten rock, sometimes also suspended crystals and dissolved gas and gas bubbles. And all of these things can range in temperature from as low as 600 degrees, which I know isn't really low, but that's pretty low compared to the high, which is about 1600 degrees. But usually it's a bit more in the middle of that range, somewhere from 7 to 1400 degrees Celsius. Now sometimes magma can percolate into adjacent rocks, so just the force of it coming up from the mantle can cause it to kind of find its way into the little cracks and crevices of the rocks underneath the surface. But other times it can flow out onto the surface, and that's when it becomes known as lava. So it's still the same substance, although of course it's undergoing cooling as it reaches the air. But now once it's above the surface of the earth, it's referred to as lava. And it can also be ejected explosively, so basically it comes bursting out of volcanoes. And in that case, it's known as something called tephra. And one interesting form of lava also is a lava fountain, and this is when lava is forcefully but non-explosively ejected. And basically I think of this as the difference between firing a bullet from a gun, which would be quite explosive, and turning on a garden hose, where you've got a lot of power coming out, but there's not an explosion causing the emanation of that water. And just like with the garden hose, you can pulse the ejecta, or you can let it come out continuously. And so lava can come out in these little bursts, or it can come out all at once in one really long eruption. Now, I also said that volcanic ash can come out of volcanoes, and ash is a small particle of pulverized rock or minerals or volcanic glass. And volcanic glass is something that's created by rapidly cooling magma, and basically where you would normally see crystallization occurring, in this case the cooling is so rapid that it's uncrystallized, and that's what results in glass. And ash is formed when dissolved gases in the magma expand as they encounter changing pressure conditions. So when they're deep in the earth, there's quite a lot of pressure and quite a different temperature. And then as they come closer to the surface, some of that pressure is released, some of the temperatures may be a bit different, and so that causes this rapid expansion and everything comes exploding out. You can also have ash formed when magma comes into contact with water and flash steams. Now, unlike magma, which generally will kind of peter out after a while because it's exposed to water and air and begins to cool and harden, ash can travel thousands of kilometers from the site of origin. So you tend to find this covering much larger distances and having an impact for much longer periods of time over much larger geographic areas. Now, the final thing that comes out of volcanoes are gases. And these are mostly steam, which of course is suspended water molecules, and also something called magmatic gas. And these include carbon dioxide and sulfur dioxide prominently, but also may have hydrogen chloride, hydrogen fluoride, and hydrogen sulfide within them. Now, hydrogen sulfide is quite interesting because it can eventually become converted into something once it's released into our atmosphere. And the thing that it's converted into is sulfuric acid. And this is important because it leads to increases in the albedo of the Earth. And the albedo is a term that refers to how much radiation the Earth reflects. And so when you increase the albedo, you increase how much radiation is being reflected, you end up cooling the troposphere, which is the section of the Earth that we live in. But at the same time, it actually can lead to warming of the stratosphere, which is the section above us. And that's because these particles increase the absorption of surface radiation that's coming up from the Earth. So they're not letting as much stuff in, but they are absorbing the stuff that's coming up from the surface. And all of this means that we begin to have quite uncomfortable living conditions. And these can result in something that's called a volcanic winter. And I'll talk a bit more about volcanic winters in a minute, but actually these are surprisingly recent in some of our history. So even just in the 19th century, the early 19th century, there was something known as, or thought to be, a volcanic winter, when there were huge periods of famine and starvation, and people did very poorly because they lost all of their crops as a result of these conditions. So volcanoes, as this suggests, can have a really big impact not just on nature, but also on human culture. Excuse me. So volcanoes are usually found at tectonic boundaries, where there are two plates that are moving perpendicular to each other. In other words, they're crashing into each other. And they're rarely found at places where these tectonic boundaries are kind of parallel. So where you've got sliding plates, like the action that happens at the San Andreas Fault, for example, in California. Now, when you have tectonic boundaries, there are two different types that you might find. The first is divergent, and the second is convergent. Divergent boundaries are where tectonic plates are pulling apart, and as they pull apart, they begin to thin the crust and make it more weak, which means that the stuff that's underneath it can come out. And where you've got places where there is magma boiling around underneath there, being pushed up by the activity down in the mantle, then of course these are going to be areas where there's going to be a lot more instability, and you can have volcanic activity. And you tend to find these pretty often between oceanic plates, where the divergence creates structures known as mid-oceanic ridges. And one example of this that's pretty nearby here is the Mid-Atlantic Ridge. But you do also find these within continents where they can create rift valleys. So for example, Africa's Great Rift Valley, and also the Rio Grande Rift in North America. Now I mentioned convergent boundaries, and these are where tectonic plates are coming together. And the movement of these plates causes a subduction zone, where one plate goes under the other, or a continental collision, where basically you've got kind of even power from both, and so they just begin to ripple each other and create mountain ranges. And one prominent example of a subduction zone is along the west coast of South America, where the Nazca Plate is going under the South American Plate. Also in California, where I recently was, the Farallon Plate was subducted underneath the North American Plate in a process that lasted several million years. And continental collisions happen, actually have happened in the past quite recently, and there are some that are still happening. For example, the Indian Plate, where it meets the Eurasian Plate, is causing the Himalayas and the Tibetan Plateau. And that's why we still see some growth of mountain ranges in these regions, because the plates are still pushing against each other. There are also some volcanoes that are non-tectonic boundary volcanoes. And these have been explained by the concept of mantle plumes. And this has received some criticism, but it's definitely worth mentioning because I think it potentially is gaining more support from what I was reading, though perhaps I could be wrong. So basically the idea here is that you've got hot rock that's rising from the boundary of the core and the mantle, and it forms structures called diapirs. And these are intrusions of the magma into overhead rock, usually because there are small fissures that the magma can be kind of pushed up into. And if you look up diapir online, you'll often find pictures of lava lamps, because you've got those globules of one color that are kind of dispersing through a background, a liquid of another color. And basically the diapir is that kind of cloudy bit that's in the middle of the rest of the colored liquid. And so that's kind of a nice way to visualize what the magma is doing, or the hot rock, underneath the surface of the earth. And one really famous example of a hot spot is Hawaii, all of Hawaii, and also the Yellowstone caldera, which I'll talk a little bit more about later on. And basically the idea here is that these places are kind of always going to be quite hot and form quite a lot of, have a lot of activity, and as the tectonic plates move over them, different spots will be exposed to this mantle plume area and these hot spots, and will then undergo volcanic activity. That was Jackson with Hot Spot, and that reminds me that I forgot to mention who was singing that first song today, and that was Jimmy Buffett with Volcano. So today we're talking, obviously, about volcanoes, and the next thing I want to go into is different types of volcanoes. You might think that a volcano is a volcano, but actually there are lots of different types of volcano, and they're formed by different types of conditions, and the type of volcano will determine the type of activity that it has, and therefore the effects that it has on an environment. Excuse me, I can't seem to clear my throat today. So the first type of volcano on my list is fissure vents. And these are usually narrow but often very long linear areas from which lava can erupt. And it's usually kind of a gentle eruption, if there is such a thing, in that it doesn't happen very explosively. And if you look at these from aerial photographs, they may look like they're just a crack in the ground or a crack on the ocean floor. And that's often because they're filled in by lava that comes out and hardens, and so it's just kind of continually replenishing itself and kind of filling in the gap that's being made by the activity there. And as erosion happens to the surrounding landscape, it can wear away the softer materials around and leave just that kind of lava ridge that has been boiling up over the years, and that is what that creates what's called a dike. And fissure vents can result in something known as a flood basalt and also a lava channel. And a flood basalt are these massive, large stretches of land that are covered by hardening lava. And you see a lot of these in Iceland, but also you can find them on the moon, for example, the Maria. And these can cover really enormous areas of land. So, for example, out in the American West, there are these entire parks almost that are covered with basaltic rock, and all of that rock, that really thick layer upon which everything else now grows and rests, all of that is lava that has just built up and then hardened. Now lava channels are, they occur where you've got some lava that begins to harden, but then other lava that keeps flowing through that. And so you've got the hardened lava containing channels of the liquid lava that keeps flowing through them. And you can find lots of pictures of these, again in Iceland, but also you tend to see them a lot in Hawaii. Now shield volcanoes are something that can often be found in conjunction with fissure vents, or vice versa. And these are formed when lava emerges from a vent and then flows over very long, large distances and eventually builds up a broad shield-like structure around the rupture. So this is not just kind of a flow from a crack and a kind of a large plateau type thing, but it does actually build up vertically as well. And the result is kind of a shield-like structure, hence the name. And these are often linked to hotspot volcanism, but can also be found at rifts and also at subduction zones. And they're found in Iceland and the Galapagos, and particularly in Hawaii. And in fact, because these were first or prominently described in Hawaii, shield volcano eruptions are also known as Hawaiian eruptions. And the size of these varies with their age, because over time you keep adding more and more lava sheets, and so the shields can build up more and more. And it's amazing, if you look at these from some angles, they look not very exciting, because that gradual accumulation of lava flows over time can mean that actually the slopes are quite gentle, and they don't rise up very high because you've just got more and more material accumulating horizontally. But from certain angles you can look on the other sides and see really large vertical steep slopes where it's kind of the opposite side from where those nice gentle areas are. And this is particularly true if you look at pictures of Mauna Loa, which is in fact the largest volcano on Earth. And this is what's known as a mature shield volcano because it's quite old. And it's amazing how you look at some pictures and you think, well, actually that's not very spectacular because you're looking at kind of the gentle side. But then you look from other views and it's really massive and craggy and quite impressive looking. And in fact, it is really impressive. So it actually rises about 13,500 feet above sea level and is over 60 miles wide. And it contains so much heavy basalt or hardened lava that it actually has begun to sink into the crust because it's more, it has more weight than the crust of the Earth can support, and that's pretty incredible. And that's a result of about 80,000 cubic kilometers of basalt that has bubbled up over time from under the Earth's surface. And then you've got kind of a group of volcanoes that kind of, you can classify them all as being the more stereotypical mountain-shaped volcanoes that you probably imagine if someone says the word volcano to you. And I've kind of loosely grouped these into different shapes and types. So there are a bunch of volcanoes that are known as domes, and these are created by viscous lava. And the first of these is what's called a lava dome. And lava domes are created when lava doesn't flow very far after it emerges from the rupture. So gradually it builds up and forms the really characteristic mound shape that we often think of, again, when we think of volcanoes. So it really is kind of the stereotypic thing where it's just a nice little kind of beehive-shaped dome. And this is different from the shield because the shield has a different type of lava. The lava is a different consistency and so can flow more. But when you've got really viscous lava, it's not flowing as far because it's thicker. And so that's why you have a more upright structure than a more horizontal structure. There's also something called a cryptodome, and this is what happens when you've got lava that's being pushed up from beneath the Earth's surface but can't break free. So instead, all of that pressure causes a bulge that can eventually create damage by undermining the integrity of geological structures. So it's pushing out through the Earth's surface but can't quite make it, and so it starts to crumble rock and bring down the mountains or whatever is sitting on top of that bulged area. A third type of dome is a mud dome, also known as a mud volcano. And these occur when you've got hot liquids and gases, in particular methane, being excreted from underground, and they form domes of various sizes. And this can be up to 10 kilometers in diameter and several hundred meters high. So these are also very impressive structures, even though they aren't quite what you think of when you think of volcanoes. They don't involve lava so much as these other things that can be brought up from underground. And you often find these things in groups. And the activity here is much cooler than at igneous volcanoes, so the ones that are expelling lava. And they tend to be associated with subduction zones. And there's actually some recent evidence that some of these are found on Mars. And that's quite exciting because the whole reason they're called mud domes is that they do involve liquids as well as gases, and all these things mix together to make kind of a muddy structure on the surface because they mix in with the dust and soil and ash around the site of the rupture. And so finding them on Mars is again more proof that there was at one time, or still is even, some water on the planet. And now another thing that you might typically think of, envision in your mind if someone says the word volcano to you, is something that I actually saw when I was out in California, and that is a cinder cone. And cinder cones are created by eruptions of cinders that eventually pile up around the vent and then create kind of big mounds around them. And cinders come in a couple of different types. You've got scoria and you've also got pyroclastics. And scoria is dark porous rock that has vesicles or pores that are formed when gases are bubbling up out of the magma during eruptions. And again, that's because of the difference in pressure and temperature. And so these are quite similar to pumice, but pumice tends to have more of these vesicles and is less dense than scoria. And pumice is also a bit lighter. So that's how you can tell these two things apart. If you float them in water, scoria will sink, whereas pumice will float. But either way, you've got this type of porous rock that can be shot out of cinder cones, and you've also got pyroclastics. And pyroclastics are rocks that are composed of pre-existing minerals and also rock fragments. And in this case, they're made primarily of volcanic materials, or even sometimes only of volcanic materials. And all of these things, the scoria and the pyroclastics, are shot out of the cinder cones, and usually they're created only in a single event. And some of these events are pretty mild, and so they don't make very large cinder cones, but other events are really intense, and so you've got cinder cones that are several hundred feet high. And indeed, the ones that we were looking at in the Mojave Desert were really impressive. I mean, I would look at that from a distance and say, you know, it's a mountain, if I didn't know any better. Of course, it's quite a bit darker colored than a mountain because it is made of volcanic cinder. But they're really high, and so when you look at that, you can really understand how much pressure must have been involved and how long it might have taken for all of those materials to come out and eventually settle around the site of the rupture in order to make that mound. And you frequently find these in quite large fields where you've got a lot of them dotting the area together. And I've got pictures where you can easily see at least a dozen of these all at once. And in fact, there are some sites on Earth where there are about 60 or so of these all together in one place. And that was Iron and Wine with Cinder and Smoke. And today on Wildside we're talking about volcanoes, and I was just going through the different types of volcanoes that there are. And there's one more that I want to mention, at least I think there's only one more, and that is stratovolcanoes. And these are also known as composite volcanoes. And these are tall mountains that are made of alternating layers of all the different stuff that can emerge from ruptures. So there's some cinders, there's some ash, there's some lava that's hardened. And these are really common at subduction zones, and they are in fact some of the most common volcanoes on the planet. So they go through alternating periods of activity and rest. And just like I was mentioning that some of these kind of dome-shaped volcanoes are the things that you might picture in your mind if someone says volcano to you, stratovolcanoes are the type of things you're probably thinking about when someone mentions volcanic activity. Because we often hear about these volcanoes that have been dormant for quite a long time, and then they suddenly become active, then they go dormant again, and you don't know when the next one's going to hit. Well, that's because they have these alternating periods where sometimes they're really active and they push out a whole lot of cinder or a whole lot of lava, and then they rest for a while, and then the next thing comes out. And that's why you have these alternating layers. They happen at different times. And these guys can be associated with some really catastrophic features and also events. And one of these is something called a mudflow or a lahar. And what these are basically you've got mud that's the consistency of concrete because it's really full of all that volcanic, thick, heavy, dense ash. And it's made of also water, and there are rocks thrown in, so just lots of nasty stuff all together. And it comes flowing out down from the volcano, and it can be incredibly deep and also flow extremely quickly. So we're talking at speeds of 60 miles per hour. And that allows them to cover massive areas much farther away from the volcano than you might expect. So distances of maybe almost 200 miles away from where the eruption actually is occurring. And what's really crazy about these is that they can happen years after a volcanic event. And so you think that everything is okay, and you know, a couple decades go past, many years go past after this eruption has occurred, and then all of a sudden all of the instabilities that the eruption has created, all of the materials that it has put out, will then allow these mud flows to begin, and they can go through and just wipe out entire villages, entire cities and towns, and they can kill enormous numbers of people. So there are many of these have happened historically that we know about, and there are tales of 30-some, 120-some thousand people being killed all in one go because of these mud flows. Something else that is associated with stratovolcanoes are volcanic bombs. And these are pieces of tephra that are greater than 2.5 inches in diameter and can sometimes be as large as entire cars. So they're really large sometimes. And they originally emerged from the volcano as lava, and they're ejected up into the air. And while they're in the air, they cool. And this is partly because they're being flung through the air, so there's a lot of air whistling past them and kind of cooling off the surface. And they're solid by the time they hit the ground, and sometimes they can hit many kilometers away because the power that has ejected them is so forceful. And because some of them fly quite long distances and are very malleable when they come out, they can often harden in aerodynamic positions. And so there are pictures of these where they've got kind of a leading edge and very smooth sides, where they've just flown through the air and been shaped by that movement. By the time they've hardened, they've shaped themselves into that aerodynamic kind of position. And sometimes, very rarely, these might explode as they cool, and that's a result of internal gas pressure. And so that's kind of an added insult that can be associated with the injury of these volcanic bombs. And finally, another thing that can come out of these stratovolcanoes is volcanic ash. And as you all know, probably from having recently experienced the eruptions in Iceland, volcanic ash can be really dangerous because it can accumulate in airplane engines. And the reason that this is a problem is that the temperature there is really high in these airplane engines, as you might expect, and it can cause the volcanic ash to melt and to accumulate and then clog up the engine. And even though we haven't had any really recent problems with this, again, this is something that we do know has happened historically. In Japan, for example, there was a problem with this within the past few decades. And actually there have been maybe a half dozen or so cases where volcanic ash is known to have caused the shutdown of these airline engines, and in all cases there was complete failure and the planes all had to make emergency landings without any use of their engines. And in all cases, everyone emerged safe and sound, which is pretty miraculous, really. Of course, the only problem, airplane damage is not the only problem. There can also be health problems associated with inhaling these things, particularly because the ash can contain some materials that aren't so great for us, as well as just generally we don't like to inhale large quantities of foreign bodies. And if this stuff begins to accumulate on buildings, it can cause structural damage. It can be very heavy, and so if you get a foot or so of it accumulating, you can bring down entire buildings. And in fact, as I'll talk a little bit more about later, stratovolcanoes have produced ash over the last many thousands of years and millions of years that humans have been around. And this ash has actually been responsible for the largest threats to human civilizations over the course of history. And we're talking about kind of natural events being damaging to us. So it's responsible for those volcanic winters that I was talking about. It's also responsible for wiping out crops and causing difficulties with breathing and bringing down villages and cities, as I mentioned. So if you want to look for any natural thing that is going to potentially threaten a lot of us all at once, this is the real source right here. Now, stratovolcanoes are also known for featuring sometimes calderas. And calderas are formed when the land collapses after an eruption. And the reason that happens is that you've got these magma chambers underneath a volcano, and they're filled, obviously, hence the name, with magma. And as soon as all the magma comes out, then there's nothing left, and they're left empty. And often these can no longer support the weight of the forms above them. And so they then collapse. And sometimes it's just a partial collapse, so you just get kind of a settling down in, but other times it's quite an extensive collapse, so you have everything kind of crumbling down into the middle. And even though a caldera can form because a lot of magma has left, they actually can still be active because there's still magma even below that in even more distant chambers. And this is the case in, for example, Yellowstone and in Lake Toba, Indonesia. And these can form what are known as resurgent domes, where you start to have the magma from beneath coming back up into that same area and then pushing and trying to get out of the surface of the earth and create another volcano where that previous activity was. And often they are successful because it is quite a weak space, it's already undergone lots of trauma, and so it's not too hard for the lava to eventually break free. Now, I just want to also quickly mention a couple of famous examples of stratovolcanoes that you might have heard about in your history lessons, and those are Krakatoa, which erupted in 1883, and that was a fairly extensive and catastrophic event that wiped out anywhere from 30 to 120,000 people. The estimates of that are currently being revised as we get more and more information from studies. And also Vesuvius, of course, you've probably heard of, which erupted in 79 AD. Now just really briefly, I do want to mention a couple of what I call hidden volcanoes. And these are volcanoes that we often don't see very easily, and so they kind of can slip under the radar. And one of these is a submarine volcano. And I've kind of talked about these in the past when I've talked about black smokers and these deep sea vents where you can have really rich and diverse communities of life underneath at very great depths the surface of the ocean. And these are typically found near tectonic boundaries, and they're responsible for the vast majority of all annual magma production on Earth. So most of the volcanic activity that produces magma that comes to the surface is actually happening underneath the ocean, so we can't see it. And you've got some really interesting differences between submarine volcanoes and terrestrial volcanoes because you've got differences in medium, so you've got water instead of air, temperature and also pressure, and this leads to magma formations that are quite variant from those that we find on the surface. You often get volcanic glass being formed, and also these really interesting boulder flows that are known as pillow lava. And basically what happens is that you've got kind of a crust that forms on the outside, but it's still kind of soft on the inside, and so later flows that are still coming out will then push into that and it will just billow up. And basically it's kind of like if you've ever iced a cake. And if you think about it, you put your icing instrument down on the surface and just keep pushing, all of that icing starts kind of forming up on itself, and it makes these little cloudy ridges. And that basically is what's happening underneath the surface of the ocean with lava. And sometimes these can be associated with pumice rafts, and that happens, when that happens, you've got pumice that floats up from underwater after an eruption. And you can see really huge fields of this if you look at aerial photographs. And actually recently, just last year, there was a really large pumice raft that was seen off the coast of New Zealand. And researchers have suggested that rafts like this can actually really help organisms migrate from one island to another, because this basically gives them lots of little stepping stones that they can use to get from one place to another, particularly in volcanic areas where the islands may not be all that far apart. Now the last type of volcano that I want to mention, period, also another type of hidden volcano, is a subglacial volcano. And this is kind of counterintuitive because you wouldn't think that something that hot would be associated with something that cold. But in fact, it does happen, and they're also called table mountains or tuyas. And these develop under ice caps, where you've got basically the ice cap is keeping the lava flow in place, and so you have these really extensive sheets of lava that are forming over top of pillow lava, which I mentioned again happens underneath the surface of the ocean, and also something called palagonite, which is a mixture of water and volcanic glass. And so you've got these two things forming deep beneath the surface, and then over top of that you've got the sheets of lava that are flowing in to fill the gaps between those other volcanic products and the ice above them. Now all of that brings me to something that you may have heard about and have wondered about and maybe even been afraid of, and that is the supervolcano. And the supervolcano is not actually another type of volcano, so it can't be given a classification like submarine or subglacial or any of these other things. It's kind of something that stands all on its own. And in fact, it's not really something that's even an official term, and it's generally only used by scientists when they're speaking to the public. And it's a word that was coined in the first part of the 20th century by American volcanologists, but then it was popularized here in the UK by a BBC show known as Horizon, and that happened in the year 2000. And since then, you see more and more references to the supervolcano. And what would actually be more accurate is to refer to super eruptions. And super eruptions are events that rate 8 on the Volcanic Explosivity Index, or the VEI, and I'll talk a little bit more about that later. But basically, the idea of a supervolcano, if you don't want to be quantitative and talk about these VEI scores, the idea is that it's just referring to any volcano whose eruptions can produce a really massive amount of ejecta. So a normal volume would be something, you can measure these by looking at cubic kilometers, which I mentioned earlier in one of the measurements. So a normal volume is maybe something below 1,000. Therefore, a supervolcano is anything that goes over 1,000 cubic kilometers. And these usually occur when magma is rising from the mantle and forms a hot spot under the crust. And it's unable to break through. So I mentioned this a couple times already. You get this pressure building up because the crust is keeping it in place, and so you just have more and more pressure building as that magma is trying to escape. And finally, after that pressure mounts for so long that the crust can no longer support it, you'll have a catastrophic eruption, and all this stuff will come spewing out. And sometimes you find these at convergent plate boundaries and continental hotspots as well, but it is generally these hotspot regions where you can have just massive amounts of magma and massive amounts of pressure. And these can have really large and long-term changes to the weather, which in turn can lead to species extinctions. And as I mentioned earlier, repeatedly, these volcanic winters. And that was Johnny Cash with Ring of Fire. And I want to continue on the topic of supervolcanoes because I think these are really interesting, and I eventually want to work up to a little case study, so I want to give you a bit more background. So there are two types of eruptions that can be classified under the larger name of supervolcano, and I think of these as kind of the tortoise and the hare. So the tortoise version is something called a large igneous province, and these are large regions of basalt that are created by flood basalt eruptions. And examples of these are found in Iceland, the Deccan Traps in India, and also the Siberian Traps. And these generally accumulate over millions and millions of years and comprise millions of cubic kilometers of hardened lava. And so basically, these achieve the name of supervolcano not because all of this stuff is coming out all at once and having a really catastrophic, huge, amazing, you can't miss it volcanic eruption, but really it's kind of a steady trickle if you think about it over geological time. And then you've got the hare version, which is the massive eruption. And these are eruptions that rank really high on the VEI scale, which I mentioned earlier. And VEI was devised in 1982 to help measure and also compare eruptions in a quantitative, well, mostly quantitative way. And this takes into consideration things like product volume, height of the eruption cloud, and also explosivity of the eruption. And researchers have identified 47 eruptions that rank at or above a VEI of 8. And most of these happened tens of millions of years ago when the Earth was still kind of young and it was forming and things were very unstable. However, there was one that occurred fairly recently as far as the age of the Earth goes, and that was about 26,000 and a half years ago. But you do tend to have lots more eruptions that occur at lower VEIs, including still quite high VEIs, so 5, 6, 7. And in fact, one of, if not the largest super eruption occurred about 30 million years ago in Colorado and was responsible for spewing out over 5,000 cubic kilometers of ejecta. So if that's the biggest thing you can imagine, then you can see how VEIs of 7, 6, 5 are still pretty intense and can have a huge effect. Now, another famous site associated with supervolcanic activity is Yellowstone. And I think this is worth a closer look because you often will hear people talk about Yellowstone in the news. It's something that's become kind of increasingly interesting, particularly because there are movies that are kind of made about this or kind of refer to it. They tend to be pretty crummy sci-fi movies, but they do have this grain of truth that is kind of interesting to explore in a bit more detail. So if you know anything about Yellowstone, you'll probably be aware that it's famous for having geysers and hot springs and bubbling mud pots. And all of these things are linked to subterranean volcanic activity. And all of that is likely caused by a hot spot that lies beneath Yellowstone, and it's known as the Snake River Plain or Yellowstone hotspot. And evidence of the hotspot can be seen all along the Snake River Plain, which stretches from the northwestern portion of Wyoming all the way to the Idaho-Oregon border and beyond. So elevations on the plain decrease from east to west. So you've got things out in the west are much shorter than things in the east, and there's also an association with age. So basically the oldest structures are in the east and the youngest are in the west. Sorry, backwards. The oldest structures are in the west and the youngest are in the east and in Yellowstone. And so you've got this association between height and age. And so likely the oldest things are the things that have been around and have been worn down, and that's why they are shorter than the youngest ones on average. And the youngest things are in Yellowstone because that's where they have most recently been formed. And if you look at the plain, you'll find that the path of it is approximately parallel to the motion of the North American plate, which moves to the southwest approximately 2.5 centimeters each year. So basically what you've got happening is you've got this hot spot, and it sits in the same place, and as the lithosphere, sorry, that's a hard word to say, the lithosphere moves across it, then you have volcanoes becoming active and allowing the magma to escape. And that's why you've got all these different volcanoes that emerge over time as they slide over top of this hot spot and undergo activity. And the initial impingements, as they're called, of this hot spot occurred in the north-central portion of Nevada along the Oregon and Idaho borders. And since then there have been 15 or 20 so eruptions that have left calderas stretching from that bit through Idaho and into Wyoming. And if you pull up a map, and I'll put a picture of this on the website, you can see this stretch of volcanic activity where one volcano after another has been triggered as the land has slid across that hot spot under the surface. And seismologists have studied wave patterns in order to try to determine the path that the magma is taking from deep in the earth all the way up to these active areas. And they're able to do this because waves travel at different speeds in different types of rock. So where it's warmer, the waves slow down. And so they're able to infer the presence of magma in these bits. And they do know that there are huge amounts of heat at Yellowstone, and it's much higher than the continental average. And again, this all suggests that there is in fact this hot spot underneath the area. Now Yellowstone has had 3 huge eruptions over the last 2 million years. These happened 2 million years ago, about 1.3 million years ago, and also about 0.6 million years ago. And if you look at those, you'll kind of notice there's a pattern that suggests that actually there should have been one already, and there should be another eruption coming at any moment now. It's long overdue. And some people say there is a lot of evidence for this, others say there's not so much evidence, and either way you can't really panic because there's not much you can do about it. But we do know that there is a lot of interesting activity in Yellowstone right now. So there have been lots of shallow and moderate earthquakes over the last several decades, including lots of little bursts of them together that are known as swarms. There's also been crustal deformation, including both uplift and then subsidence. So there was something pressing out on the crust and then it shifted back into place, suggesting kind of a change in how much pressure was underneath the surface. And there are also differences in kind of the temperature and pH of some of the waters there, suggesting that different things are being released into the soil and the water from below the earth. And another eruption in Yellowstone would be catastrophic, not just locally but around the world, because again it's going to have that volcanic winter effect where you've got changes in temperature, you are potentially exacerbating the greenhouse effect, you've got ash coverage, and you're going to have a loss of life, a loss of structures, a loss of crops, all sorts of bad things would happen. However, there is also some evidence that Yellowstone is beginning to expire, so that portion is beginning to shift off of the hot spot and another one will come. And if you've got a shift away, then you're going to release that pressure because you'll start again on a whole new place where you start adding the pressure until it eventually builds up. And if that's true, then maybe we aren't going to have another eruption. Yellowstone will become dormant, and then in the next 1 to 2 million years, you'll eventually build up enough pressure to have another eruption in this area. However, I just want to point out, in case anyone is now panicking over this thing that I think is interesting but might also be quite terrifying, that things can actually, go on even if these sorts of eruptions occur. So about 70,000 years ago, for example, there was a super eruption at Lake Toba in Indonesia, which I mentioned earlier. And this is one of the largest known volcanic events that ever happened. And it resulted in a volcanic winter that lasted 6 to 10 years, and then a cooling of the climate that lasted for about 1,000 years, researchers think. And as a result of this, some biologists who have studied human evolution have suggested that these extreme conditions nearly caused humans to go extinct. And lots of people died off. It only left a few people behind. And this created a severe bottleneck that altered our genomes forever because there were so few people and so few genes. It really dramatically affected what was left in our genome when people then bred. However, regardless of what happened, we did survive. We made our way through it. So even if Yellowstone or any other supervolcano does blow, we're likely to hang in there even though it might not be so pretty. So rather than panic, hopefully you'll find all of this information interesting and intriguing, and you might be inspired to go to Iceland or Italy or California or any of these places that have these really dramatic and interesting and incredible landscape features that you just don't see every day. And I certainly had a fun time seeing them out in California, and I hope that you have learned, as I have learned, about these really interesting things. And with that, I'm going to end today with a little bit of Beck singing Earthquake Weather, and I'll put all of this, as always, on the Wildside webpage. And that's it for now, so I'll talk to you next week.